Hello, my name is Janice Asante, and I had the red mechanism for the teacher mechanism assignment. Only 2 residues in the active site were required for catalytic activity. Loss of aspartate 45 resulted in 35% activity. Loss of aspartate 63 resulted in 30% activity. So what that basically means is that instead of where we want to be, 100% activity, if we lose those aspartates in our reaction, it's going to be at 35% activity or 30% activity for those specific aspartates we're losing, which means that the reaction is going to slow down significantly if we lose those aspartates, which likely means that those 2 aspartates are the 2 residues that we need in our active site for catalytic activity. Our pH profile for 100% activity, the reaction will be operating at pH of 4. So that means that our reaction is likely happening at a pH of 4. Here are 2 aspartates. We know that aspartates have a pKa of around 3.7 for the side chain. When pH roughly equals pKa, we know that 50% of the residues will be protonated and 50% of the residues will be deprotonated. What this tells us is that the deprotonated residue is likely going to be used as our general base, and our protonated residue is likely going to be used as our general acid. We know that this is a hydrolysis reaction because we're opening up a ring. Since it's hydrolysis, we need a water. To start off this reaction, let me highlight our nucleophile in pink. So here is our nucleophile, this water. And then I'll highlight our electrophile in green. Here's our electrophile in green. Starting off our reaction, we want to make sure this water is a very good nucleophile. We want it to be a little more electronegative than that so that it can attack our electrophile. So we're going to use our base to grab this hydrogen. It's going to move the electrons onto the oxygen, making it more electronegative to attack our electrophile. That attack is going to push these electrons up onto the oxygen. The oxygen is going to reach down for a hydrogen to stabilize this reaction. Okay, so now we have a tetrahedral intermediate with 2 hydroxyl groups. Our aspartate 45 is now protonated, and our aspartate 63 is now deprotonated. We want to kick off this nitrogen, or this amine group, to open up this ring. To do that, we want to close our carbonyl back, push the electrons back. The electrons are going to come down because of that push and go back to the carbon-oxygen bond. Because that happened, we're going to have to push electrons back onto this nitrogen. So to stabilize itself, it's going to grab hydrogen from this other aspartate, and we're going to push our electrons back onto this oxygen. We have a carboxylic acid. The ring has opened, an amine group, and then we have a protonated aspartate 63 and a deprotonated aspartate 45. Okay, and because we know our reaction operates at a pH of 4, carboxylic acids have a pK of around 3, amines have a pKa of around 10. At pH of 4, amines will likely want to be protonated. Carboxylic acids will likely want to be deprotonated. We're going to have the amine group take a hydrogen from the solution, water. It's going to push the electrons back into the water, and then we're going to have the carboxylic acid donate a hydrogen to the solution. As a result, we're going to get our final product. You can see that our enzymes have been regenerated at the end of our reaction. Now, I want to talk about some of the catalyses that are happening in this reaction. So we know that we have base catalysis because aspartate is acting as a base. It's grabbing a hydrogen in order to facilitate the reaction. And we also know we have acid catalysis. Aspartate is also acting as an acid, donating a hydrogen to facilitate the reaction. We also will be experiencing the proximity effect because just the proximity of these 2 residues in the active site to the substrate will also facilitate the reaction. And we also know that this is a sequential mechanism because of the ternary complex that is being formed between aspartate 45, the water, and the substrate.